Good afternoon, Professor Sarmin. How are you today?
Good afternoon. I'm fine, thank you.
Okay, I would like to greet everyone else. Good afternoon, everyone. I hope you are all doing great. Thank you for joining us today for this exciting session on decoding linear transformation. I'm Calvin Miner as a lecturer in mathematics department at Bina Nusantara University, and I will be your host for today. So today we are honored to have with us Professor Dr. Nur Haniza Sarmin, a renowned professor of mathematics from the Faculty of Science at University Technology Malaysia or UTM. Today's session will focus on linear transformation using factors and matrices. And I'm sure we will all gain valuable insight from Professor Dr. Nur Haniza Sarmin's expertise. So I think we can start our session now, but before that, maybe I will make Professor as the host of this meeting, so it'll be easier for the professor to share the material. Wait a second. Oh, I think you already a co-host.
Yes.
Okay.
Okay. You, Dr. Kelvin?
Yeah, I'm Kelvin.
Okay, Kelvin. Okay, thank you very much, Kelvin. Good afternoon, everyone. Assalamualaikum.
Good
So we
afternoon.
have around 200 of you here who are all students, or they are also non-students. Guys, if you can just 1 minute, turn on your video. Can I see your faces?
I think mostly students here.
Okay, just 1 minute, guys.
Yeah, guys,
Very
feel
nice to
free to
see the
open
real
your
person.
camera.
Okay. Okay. They come from many campuses?
Yeah, I think
Or just from one campus?
for several campus.
Several
I don't
campuses.
know. Yeah, because the invitation was sent to every campus in
Every
BINUS.
campus.
Yeah.
Okay. Okay, it's very nice to see everyone. Okay, guys, if you did not turn on your video, you can do the reaction to my question, yeah? Because before start, I want to ask simple questions, including you, Kelvin. Okay, you can click reaction, the this or this, yeah? Okay, I think you are familiar with Zoom. I just want to know, not raise hand is asking question. Raise hand is asking question later. So how many of you have been to Malaysia? No, none. Ah, I see one hand down. Okay. Okay. Not that many. Okay, I have been to Indonesia several times. BINUS in Jakarta and others, right? And I'm also planning to go to ITB in August. So stop by in Jakarta and get the whoosh, right? The train. Okay. So not many. So I hope, although you are here with me here virtually, then hopefully you will come to visit us, maybe in Malaysia or in UTM. Before I start with the linear transformation, let me share. Okay, hold on. Let me share my screen. Okay. Let me close everything else. So many things that I see here. Okay. You see my first slide, Kelvin?
Yes, Professor.
Which is the poster, right?
Yes, the poster. Yeah.
Just the poster.
Oh no. Actually, it's I can see the next slide of
Okay, okay,
yeah.
okay. Let me, now just one slide.
Yes.
Okay, I cannot use two screen then. All right, so thank you for the invitation. Okay, and I think you have heard about, because you're taking linear algebra class, right? So chapter 1, you have learned about matrices. Chapter 2, normally in UTM, we learn about system of linear equation. Okay. Chapter 3 is about vector space. This is the normal syllabus. And chapter 4 is linear transformation. If you have also taken cryptography, you will learn about encoding and decoding. Encoding is you do it as a code. Decoding is from the code going back to the reality. So let's see whether my presentation is decoding linear transformation. All right, but first, let me bring you to UTM. Okay, this is UTM. This photograph is taken from the third floor of my building of my office. So if you go out my office, then you can see the mosque. The mosque is in the middle of UTM. And this is where you are, right? Everywhere in Indonesia. Okay, this is where I am right now. That's Malaysia, right? So about 2 hours to Malaysia. The West Malaysia and the East Malaysia. And this is where I am right now because UTM has 2 campuses. You might have been in Malaysia, maybe to Kuala Lumpur mostly, but the main campus is in Johor Bahru. And Johor Bahru is in the state of Johor, which is actually just across Singapore. You can actually particularly walk through these streets, Calvin. That's not that far away, okay, from Singapore. Okay, I'm not sure if you are probably in School of Computing or Mathematics or Science. We are from Mathematical Sciences in Faculty of Science. And also we teach linear algebra in School of Computer Science in Faculty of Computing. And also some students, last week just, we have this Faculty of Artificial Intelligence in UTM, the new faculty. Okay, and about our department, who knows, you might continue your study, right, in UTM. Right now, you are in undergraduate, so we have these 2 undergraduate. We also have masters and PhD students. We used to have around 1,000 students from Indonesia studying in UTM for undergraduate and also for masters or PhD. This is my research, which is in applied algebra and analysis group. So just as the introduction, because later on I will share about the application. But just to share you some photos, you might know Dr. Alfie, right, Kelvin? Your head of
Yes.
department.
Yes.
She visited us actually at the end of November of 2022. So this is my office previously in the international office. This is Faculty of Science. That's the mosque from the other side. Okay, so you take photo here. This is where I am right now, my office in the faculty. And this is where we bring her to our convocation. So we also have bakso berapi beranak. So, something in Malaysia which is very close to Indonesia. As of my background, this is where I studied last time for my bachelor, master's, and PhD. I will stop here the slide because later on I will share again the application, but we go back to the reality and I will use my I will use my whiteboard. Let me do this so I can see myself. Okay. And this. Everyone can see my whiteboard. Yes.
Yeah.
Okay. Kelvin, you have to always turn on because you will be the one answering my question today, right?
Okay. Okay.
Okay. Okay, questions later. Then you can help me also, Kelvin, to reply the question in the chat. Okay, let's see. Linear transformation, right? This is our topic today. So within 1 hour, I will share a little bit about linear transformation. Now, we need to have the definition of the linear transformation. So, definition. How many of you have learned about linear transformation in your linear algebra class? Yes, no? Okay, I will assume even if you have, then you will see it again. So, if we have a mapping, or we call it a function, from T, from a vector space V to a vector space W, right? So V and W are vector spaces. Okay, Kelvin, I know you are teaching also this, but since students might be quiet, so let's remind everyone, refresh everyone's memory. What is a vector space? What is a vector space? Anyone wants to reply? Yeah.
Can I try?
Yes.
A vector space is a abstract space that contains vectors. So, for example, functions.
Okay.
We can describe functions as vectors, right? Since they follow the properties of additivity and scaling.
Okay. So vector space, we just recall is a non-empty set, right? And it has operation, right? Non-empty set with operation in the vector space, in the set, in which we have 10 axioms, right? 10 axioms. So it has to be closed. You have to be U plus V is V plus U, right? And we also have the identity, we also have the inverse and associative, all those, you have learned about that. So that is our vector space, V and W. So now we are looking at a mapping from one vector space, V, to a vector space, W, and we call it a linear transformation if it satisfies two properties. So the first property is T of U plus V is U plus TV. And this is for all U, V, in V, and I will use C in R. Okay, that's the first property, meaning the image of the sum of the vector in the vector space is the sum of the image. Okay, and the second one is T of C is a scalar, just a number. T of CU is C of T of U. So these basic two things makes it linear. So I will share some examples on transformation which is linear and also some transformation which is not linear. And the second part I will share about some applications of the linear transformation. Okay, the one answering just now, you mentioned about function. So what kind of vector space that you have learned so far? Okay, let me get a check. Okay. So, yeah.
One example is the vector space of polynomials.
Okay, good. So number one, for vector space, we have the easiest one. Normally, we talk about the Rn, right? R is real, R2 is R cross R, which is the XY axis, right? A pair of real numbers, or R3, XYZ, and so on. The second one is polynomial. So the set of polynomials also will create a vector space. What else? Matrices, right? Matrices under addition. It's a vector space. And also, I'm not sure if you learned, but you mentioned just now that continuous function. Okay, continuous function is also a vector space. So let me give you example of linear transformation. Okay. Okay, let me go this way. Right, so for the examples. Now, I want my transformation is from T from R to R squared. Okay, and I have to give you that formula. What is T of X? T of X is X0. Okay, can somebody tell me what is the image of 1? What is T of 1? T of 1 will be 1, 0, right? T of 2 will be 2, 0. That is how you translate or map from R to R squared. From one number to 2 pair. So this is the linear transformation. So how do we show this is actually a linear transformation? So we will do this next. So I will erase this. Okay, so you have to show this and you have to show this. So for the first one, okay, we want to let X, Y in. So you have to show, I don't use UV because this is X, so I just use XY. Okay, so T of X plus Y equal, what is T of X plus Y? You replace here, so it becomes X plus Y 0. And we have to show that this is equal to Tx plus Ty. And what is Tx plus Ty? Tx is X0, Ty is Y0, right? So you see that you have to separate into 2. So this is X0 plus Y0, which is actually equal to Tx. Tx is X0 and Ty. Okay, so this is how to show something is linear. The second one, I will write here. You have to show Tcx is Ctx. So what is T of Cx? So you replace x with Cx, you get Cx 0. You have to show this is equal to C times Tx. So meaning you have to take out the C. So you take the C out. And what is X0? This is Tx. So you see, you have shown Tx plus y is Tx plus Ty, which is this. And T of Cx is Ctx, which is this. So you conclude T is a linear transformation. It's quite easy if you know what is your UV here. Your UV, don't forget that UV is in V, and then you just follow and use the definition. Okay? Let me give you the second example. Second example with a different vector space. Okay. So the second, any question here before I erase? Everything is clear, yeah? Okay. Kelvin, you really have to help me if somebody raise their hand or if they write in the chat. You are welcome to turn on your microphone and ask me question because I cannot really see everyone. Okay.
Okay, Professor.
All right. Thank you. Okay. So, number 2. Example 2 will be T is a mapping from 2 by 2 matrices into R. Okay. And let me give you such that a matrix, okay, now it's a mapping from a matrix to a number. So let me define T of A, B, C, D is A plus D. Okay, before we start proving, let me ask you, what is T of 1, 2, 3, 4? What is the answer? What's the answer? T of A, B, C, D is A plus D. What is
5.
T? Yeah.
This is the trace of the matrix, right?
Yeah. So you just add up the diagonal, right? So this is just 1 plus 4, which is 5. You see, this is like a machine. Linear transformation is like a machine in which you put in the input are all matrices, then the machine do the process, actually adding the diagonal, and what is out? The output is a number, right? This is like a machine. Let me give you one more. What is T of -1, 0, -2, -3? What is your answer? What is your answer? -1 plus -3, which is equal to -4. Okay, so you have to understand what is the definition before you can do your proving. What you put in has to be matrices. What comes out has to be a number. Okay, so now this is optional. I'm just giving you what it means by the transformation, but now we need to prove this too. Okay, to prove this too, let U, because I want this to be U, is the matrix A, B, C, D. And then I want another matrix. You can put E, F, G, H. You can put that, or you can put any, whatever you like, or A prime, B prime, C prime, D prime. So let me just put E, F, G, H. Okay. Then I will write here what is U plus V. So you learn how to add matrices, right? So you just add these two matrices. So A plus E, B plus F, C plus G, D plus H. Okay, now what is the first one? The first one, you have to write what is the T of U plus V. So I already calculated U plus V. I just put T of that. Okay, now we want to find the image of one matrix with the formula. If you have a matrix, the machine will add up the diagonal. So this is A plus E plus D plus H. Now you have to show that this is equal to separately, right? Then you think inside your head, what is T of U? T of U is A plus D. What is T of V? T of V is E plus H. So you see, there's a A plus D here, and E plus H and they are just numbers, so you can rearrange. They are just numbers, so I rearrange because A plus D, I know it's T of A, B, C, D. And E plus H is T of E, F, G, H. Right? So this is just rearrange, and then this is just by definition A plus D. Go back, right? Go back. So you get this and that, which is actually TU plus TV. I hope you can still read that, very small. Okay, so this is how you show the way by replacing what is your U, what is your V, right? The second part I put here, T of CU. What is your CU? Just now this is, oh, I cannot use C because there is a C inside. So use K. Okay, I cannot use C because there's already C here. So what is KU? So this is T, K, and my U, right? Which is T of KA, KB, KC, KD. What is T of a matrix? You add up the diagonal. So I add up the diagonal. Then what do you want to show? You want to show by taking out the K. So you factor out the K. You get A plus D. And go back from A plus D to the original one, which is T of, K, T of E. So, sorry about the space, but T of KU is K of TU, right? Okay, that's not the question. So that is number 2. For number 3, is it clear? Okay. All
There's
right.
a question.
Miss, I have a question.
Yes.
Are derivatives linear transformations? Are derivatives linear transformations?
Derivatives.
Yes.
Okay. Let's see. Let's see. It's a very good question. For example, so your T is from what? Your T, for example, from F to F, right? Okay. Let me maybe give you T of F is, this is what you mean, right? Yeah. T of F is F prime. For example, if you have Fx is sine x, so F prime x will be TF, T of Fx, which is just the prime, which is cosine of x. One example of the T prime. Okay, now we have to check. You have to check the two things. The first one, now I want to let F, G in F. Okay, now you have to show T of F plus G. Is it equal to TF plus TG? Right? So you take this side, T of F plus G, T of F plus G with the derivative F plus G prime. The derivative of the sum is the sum of the derivative, right? So this is F prime plus G prime. which is TF plus TG. Okay, that's number 1. And for number 2, T of CF. Now you have CF prime. And by the rule of derivative, you take out the constant, right? Like 2 sine x. Okay, the derivative of 2 sine x is 2, the derivative of sine x. So you have C f prime of x, which is C of TF. So T of CF is CTF, and T of F plus G is this. So to answer your question, yes. Yeah, the derivative is a linear transformation. Also, you can try with the integral. The same thing. You integrate F plus G is the same thing as integration of the sum is the sum of the integration. And also
Yes, and if I'm not mistaken, since the integral is an inverse operation on the derivative, we can define the integral as the inverse transformation, right?
yes, that's true. You have to be careful with the plus C. Okay. All right, that's good. You want to see more examples? Okay. Let me see. Time flies very fast, eh? 30 minutes already. Okay, let me give you just one more example, which is from R3, example 3 to P2. Okay. And T of ABC is AX squared plus BX plus C. All right. Okay, now can someone give me what is T of 1, 2, 3? So T of 1, 2, 3 is x squared plus 2x plus 3. So you put in, oh sorry, I need another parenthesis here because this is just for x, right? You put in R3, it comes out a polynomial. You put in a triplet of number, come out to be polynomial. So to show, this is just to give you an idea what that means, but you have to show T of U plus V. Okay, so I will let U is A, B, C, V is D, E, F. So U plus V is A plus D, B plus E, C plus F. Okay. So you take 2 U and V from R3. So what is T of U plus V? This is T of A plus D, B plus E, C plus F. Now you get an input of 3 triplet, and the output is A, which is A plus D, x squared, plus BX, B is B plus EX, plus the last one is C plus F. Now you want to show this is TU plus TV. What is TU? TU will be AX squared plus BX plus C. What is TV? That will be DX squared plus EX plus F, meaning multiply out AX squared plus DX squared plus BX plus EX plus C plus F. So you know you have to rewrite, right? You take AX squared, BX, C, and the other one is DX squared plus EX plus F. And this is actually T of ABC plus T of DE F, right? Which is TU plus TV. And the second one, you have to show, you can use K, you get the right? T of KU is T of KU is KA, KB, KC, right? K times U, and KA, KB, KC, you give a T, it becomes KA squared, KAX squared, KBX, KC, and you know you have to show is equal to K of TX, so you have to take out the K, which is K, right? Take out the K, and what is this? This is exactly just T of ABC, which is T of U, right? So you cannot go from here, here, and direct to here. You have to go through the definition. Okay, so that is linear transformation, and that is some examples of linear transformation. Okay, everyone is okay? Okay, next is another important part of linear transformation, which is called matrix transformation. Matrix transformation. Now, what does it mean by a matrix transformation? Now, this is a transformation T from Rn to Rm, okay, and M positive integers, and T of X is Ax. Okay, T of X is Ax. Now, what is the dimension of A? X is in Rm. X is in Rm, and Ax is in Rm, so A has to be M by N matrix. Okay, M by N matrix. Now let's see why it's a linear transformation. So we have to prove. Number one, so I let X, Y in Rn, then T of X plus Y, okay, it's a vector, yeah? A, X plus Y, a matrix times a vector is Ax plus Ay, which is Tx plus Ty. So directly you get the first one, okay? Then you go to the second one. The second one, T of Kx, T of Kx, Kx is A times K times X. Now you have a matrix, you have a number, and then you have a vector. Then you can take out the K outside, right? Because it's just a number. A of X, and A of X is X. Okay, you don't need to know what A is or what is N and M. This can be shown in general. Okay, this is one of the linear transformation which has so many applications for matrix transformation. I will let I will share some applications later. But let me give one example. Yeah, let me give one example. I think this is clear. Yeah, this is okay. Okay, I see so many cute. What do you call that? The emoji or what you call it? I don't see the face, but okay. Now let me see if I can give you one example. Okay, let theta be a fixed angle. Let theta be a fixed angle. And I want my transformation R2 to R2. Okay. Now for V to be XY in R2, I write as vector, yeah? R2 as vector R2. And I want it to be a matrix transformation. TV is AV, and I give you the matrix. A is, let me give you this matrix. Cosine theta, negative sine theta, sine theta, cosine theta. Okay. Now I want you to try and find the image of T of 1, 0, T of 0, 1, T of 1, 1. What's your answer? TV is AV. Theta is 90 degree. What is your A? What is cosine 90? 0, right? Right? 0. Sine 90 is 1. So negative 1, 1, 0. Okay, so T of 1, 0 is A of 1, 0. When you multiply, you get, oops, 0, 1. So that's the image. This is 0, 1. And you get the second one, right? Negative 1, 0. And the third one, you get negative 1 and 1. Okay, chapter 1, you learn about matrix multiply, right? Now let's try and draw. Okay, let's try and draw the original vector and the image with this matrix. So, if you draw X and Y axis, okay, let me get another color. Okay. This is 1, 0. Now the image of 1, 0 is 0, 1. So what happened to it? It's a rotation 90 degree. Our theta just now is 90 degree. Now the second one is 0, 1. 0, 1 is this. Becomes negative 1, 0. This is another rotation 90 degree. 1, 1 is here, right? 1, 1. 1, 1. It becomes negative 1 and 1, which is here. So also That is actually 90 degrees. So this given rotation with the matrix that I already erased is a counterclockwise rotation of 90 degree. Okay, that is one. Then you can do with different theta, and it will be counterclockwise with different theta. Okay. Next, I want to define a linear operator. Linear operator, what does it mean? Linear operator is just when the linear transformation is from the vector set V to itself. Okay, so instead of you call it linear transformation, you call it linear operator, meaning it's a transformation T from V to itself, to V. You don't change from V to W. So it's just a name of that. And let me, just now, this is a linear operator because we go from R2 to R2. Okay. I will show some application regarding the next one. So I have to give you some example that is using this. Then you can see later where we can use that. T from V to V. Okay. T of V is K times V. And K is just a real number. Now, if my V is from R2 to R2, I will have that kind of vectors, okay? Now, when K, this K, is from 0 to 1.
Professor,
Then, yeah,
there is a question.
yeah. What is the question? Geoffrey, you can turn on your microphone. Yeah,
Maybe he accidentally hit the button.
Oh, okay. So you can press again the raise hand button down there, Geoffrey. So lower hand. Ah, okay, it's okay. Then T is called a contraction on V. Okay. And if K is bigger than 1, then T is called a dilation on V. Okay. Now, as an example, okay, this is your V, X and Y. Okay. When you multiply by K is a half, you will get K is a half, you get half, shorten, yeah, contraction. But if, for example, K is 2, so you get 2V. So you expand the vector. So this is a dilation. Okay. I mentioned that I will also give an example of a non-example, meaning something that is not linear transformation. Okay. So I call it non-example, which is example of a transformation which is not linear. Okay. An example of a transformation which is not linear. Okay. You tell me why. T is from R2 to R3. Now, T xy is x, y, x plus y plus 1. Can someone tell me why this is not a linear transformation? Okay, you can try either one because you have to show two things, but you can try either one. So maybe you can let u to be xy, v, maybe I use like this, yeah? So u plus v is x plus x prime, y plus y prime. So t of u plus v is t of x plus x prime, y plus y prime. And that formula said, if you have xy, you go to three component, x, y, and the third one is x plus y plus 1. So you have the first component, the second component, and then the first plus the second plus 1. Now, it's not that straightforward to show this is not equal to tu plus tv, but you can do from the right-hand side. So you can see what is actually tu plus tv. This is t of xy plus t of x prime y prime. Okay, I replace u, I replace v. And what is t of xy? This is xy, x plus y plus 1. What is this one is x prime, y prime, x prime plus y prime plus 1. What happened when you add these two? This is x plus x prime, y plus y prime. That's the problem, yeah? This is x plus x prime plus y prime plus 1 plus 1 is 2. And this is not equal to this. So you conclude that t of u plus v is not tu plus tv. T is not a linear transformation. Okay, this is showing the first one in general. You can also show the second one, but you take k equals 2. Don't take k equals 1, you'll get it right. Take k equals 2, you multiply by 2, then it becomes x plus y plus 2. Something like this, right? Or you can just take one specific example for this. Maybe you take 1, 0, 0, 1, or you take not xy. This is also okay. Because not true in specific, it means it's not true in general. Yeah. So this is one example of something that is not a linear transformation. I don't have much time to go into the other example, but I will just write it out. You will see it's very easy to see why it's not. Okay, I just give, but I don't prove, yeah? So this is from 2 by 2 matrix into polynomial. Okay. And why? Because there is a plus 1 at the end. So when you add plus 1 and plus 1, you get plus 2, right? Like before. That is why it is not. Another one example is from R2 to M2 by 2. So this is another method from R2 to 2 by 2. And example is if I have XY, and this may be XY, YX plus 1. So you see, there's a plus 1. So anytime in the formula, you have like plus 1 or plus 2 or any number, and most probably, most likely, it is not a linear transformation. Okay. Kelvin, I wanted to mention a little bit about kernel and range, but I don't have the time. Maybe when this student went back to the class, okay, the lecturer will touch on the kernel and the range, but I want to share something else from my slide very quickly. Okay, maybe within 10 minutes or so. Okay, share screen. Where is my PowerPoint? Can you see the application? Someone? Yes.
Yes.
Okay. So some applications that I wanted to share of linear transformation in the real life. I mentioned about matrix just now, yeah? So you will see the transformation that we have comes from being matrices. You see this box is very small, then you can transform into something bigger and slanting. And they can use this like for movie. Sometimes we see little thing becomes big. The back of the movie, all those graphic is linear transformation. Another one is the shear, the one that we mentioned about the matrices. So if you have, they call it shear in the x-axis. So you just stop the down there and you pull the up, okay? And the shear in y, you fix the y and you just bring up or anywhere. They can go from the original and then you can do it. Sometimes we watch cartoon, right? And the cartoon, they have different shape. If you look at computer graphic and game development, they also use reflection, right? If our matrix that we multiply is the reflection, there's the original, the reflection, they can reflect underneath and then they can rotate. Then we have some rotation just now when we multiply by matrices. So this is how they do in the game, yeah? And the shape, when they are building the car, they want to see different shape and whether this is fast. I think you watch the movie Fast and Furious, they have different kind of cars. You can actually look at the scaling of this one. The next one is in machine learning. And nowadays people talk about all the computer scientists, they do the machine learning, they do AI. So they have the input and then they have like the machine I mentioned to you, right? You have the input and then the machine and then the output. So the encoder where the inside and decode things and you look at the linearity in the network. So sometimes these people, not mathematician, they actually use all the theoretical stuff from the mathematician. And sometimes they do prediction of the output in the firms, sometimes without realizing it. There's lots of applications on that one. You can read through this machine learning in detail. I'm not sure if you are in the computer science department, you will have specific courses, right? In the feature engineering, what do they do? In the principal component analysis, they have this linear transformation and linear regression, and also the convolutional neural network. Yeah, CNN, you can look it up later. I want to share some research that is being done right now in UTM by our colleague in the School of Education, Dr. Halim and his student, they are looking at the ethnomathematics. I'm sure you know about kuda kepang, right? In Indonesia, you also have kuda kepang, right? So for this kuda kepang, if let me see if this works. Let me see my look at the movement. If you have not seen before, this is your first time, you have seen this before, then you're seeing again. When they dance, this kuda kepang, you look at the steps. When they go to the steps to the front, and then they rotate, and they go back, right? One step, and they rotate, and they go back. After this, Calvin, you can try kuda kepang.
Sorry, Professor. I think the video hasn't shared yet.
Oh, you don't see the video?
Yeah.
Okay, sorry. Okay, let me just share directly the video. I think the Chrome did not come out. Let me try it again. Wait a second. I think I have to share the Chrome, yeah? This one. Now, can you see the Chrome?
Yes, Professor.
Okay, sorry. Okay, I think you have seen kuda kepang before, also in Indonesia. So we look at the steps. So when they dance, the steps are the same, right? They go one to the right, and then they rotate, and then one to the right, until they go, and then it follows from the other. So they are looking at this dance, they call it ethnomathematic. And then, let me try the other one. Okay, let me go back and click this, but I had to stop sharing because you don't get to see from this. Now, can you see the animation?
Not yet.
Oh, okay. Okay. Okay, let me try again. Share screen. Chrome. Can you see the animation?
Yeah.
So this is what they're doing. I mean, with the school in which, let me go back. Okay. You do GeoGebra, then you can see the translation of the kuda kepang. This is the very beginning of their research. Yeah. And then let me show one more before I stop. Okay. Let me share first. I don't know what I'm sharing right now, but let me see my slide first. PowerPoint. You see the animasi gambar penari?
Yeah.
Okay. You have Zapin in Indonesia?
I don't know.
No, okay. Zapin is very traditional dance that is famous in Johor. Okay, so let me click here. But I have to share, yeah. You see the Zapin? Okay.
Yeah.
This is what we call tarian Zapin. So the Zapin dance. So they do this and the step, and then they go around, and we have very similar. I think Indonesia also have your traditional dance. Okay, let me stop that. Because let me stop sharing and share again. Because this is, you see now the putaran. So that is how they do for this one. Okay, let me go back and stop that. Then I last of my slide. Okay. Then they do this animation. So to see the real, they never think about actually they're doing linear transformation, right? Okay, that is actually my last slide, Kelvin. Thank you very much, everyone. This is my email, actually, if you want to write to me. This is my website. You can see my research, my papers. And if you type Niza Sarmin in YouTube, you will see my classes. So during the COVID, I had, I think, discrete mathematics or linear algebra all in YouTube, yeah, and my LinkedIn. And this is the photo of our lake inside UTM. So you have seen the moss from many angles. With that, thank you very much for this opportunity. Kelvin, I pass back to you, and I really hope that if you happen to come by to Malaysia and UTM, you just say, let me know. Maybe you can
Okay.
say hi in person.
Yeah, sure. Thank you, Professor. Okay, thank you so much, Professor, for that enlightening presentation. So I guess we will now open a session for any questions. So if any student have any questions, please open your microphone and we can discuss it here, or maybe you can type your question into the chat. Maybe we will wait about 1 minute before we closing.